Okay, so the next couple topics this week, we're going to be working with two variable um, um, graphs and statistics. Um, and when we've worked with two variables before, we've done graphs and statistics with one variable at a time. But this week we want to sort of see the relationship between the two variables. We're going to be doing graphs and statistics that show the relationship between variables. So here we have data from 10 different babies. We have two variables, gestation or length of pregnancy, and we have the birth weight. And because the pregnancy happens before the birth, I'm going to make that the x variable. Usually x variable, if you have one variable that causes another variable, or if you have one variable that comes earlier in time than another variable, that variable will be the x variable. That's also called the independent variable or the explanatory variable. And then the other variable is going to be the y variable, referred to as the dependent variable, or the okay, so the type of graph that we're going to be working with here are it's called a scatter plot. And so for each of these babies, we have two different numbers, and frequency was okay. So and so we're going to have two different scales here. So the highest gestation, I think, is Wendy, which is 42 weeks. So the X scale has to go at least up to 42. It could go a little bit past that. The highest birth weight, Wendy, 122 ounces. So that the Y scale has to go at least up to 122. Usually, I like to start the X scale from 0. That makes it easier to read from the graph. Use the graph to find the y-intercept. So it usually it's a little easier if I start the X scale from 0. Most of the time, I also start the Y scale from 0, but I think it's not as important where we start the Y scale, as long as it includes all of the data values. Okay, so then once we've made the scale, then we can start plotting the points. So Quincy is 39 to the right, up 104. So at 39 to the right, up 104, maybe about right here. And then Rochelle, 40 to the right, up 100. 40 to the right, up 100, maybe about right here. And so forth. So I'll plot each of the points. And and then we can use that to describe the graph. So when we're looking at a scatter plot, we're not usually looking at symmetry versus skewness. We want to know, are the graphs close to a straight line? In another course, if you go on to take more statistics, you might try to fit the graph to a curve that's not a straight line, but in this course we'll be mainly concerned with whether the graph is close to a straight line. So if the graphs are kind of spread out all over the place, or if they're close to a straight line with no slope, or slope 0, then that would be little or no correlation. If they're close to a straight line with a positive slope, but they're kind of moderately spread out, that would be moderate positive correlation. If they're close to a straight line with positive slope, a strong positive correlation. And later we'll be computing the correlation coefficient. If there's little or no correlation, the correlation coefficient R will be close to 0. Moderate positive correlation, R is between 0.3 and 0.8. Strong positive correlation, R is between 0.8 and 1. And if they're exactly on a straight line, it might be that there's a deterministic rather than a statistical relationship between the two variables. In that case, r would be exactly equal to 1. So r measures how close the dots are to a straight line. And the sign of r is going to be the same as the sign of the slope. In this bottom row here, we have a pattern, but it's not a straight line type of pattern. It's probably r is going to be close to 0 here, little or no correlation. We have on the left side we have a negative slope. On the right side we have a positive slope. So they kind of balance each other out. So there's little or no correlation there. In a different course, you might be able to fit a curve to that set of dots. But here we're mostly working with straight lines. The next example, we have a moderate negative correlation. It's moderately close to a straight line with negative slope, a strong negative correlation, and then again a deterministic relationship with r close to -1. Okay. An example of a deterministic. So anyway, this graph here, it appears that there's going to be I would say it's a strong positive correlation. If you want to call it a moderate positive correlation, I would accept that too, but they seem fairly close to a straight line to me. They're not exactly on the same straight line, so it's not deterministic, but they're pretty close to a straight line. Example of a deterministic relationship would be the temperature conversion formula from Fahrenheit to Celsius. This is a linear equation. You may recognize the slope 5/9. If you're multiplying by 5 divided by 9, so it's a linear equation. Okay, so just some comments. Okay, we're not. We'll be computing R in a different lecture. I'll go over how to compute R, but for right now, I just want to summarize some characteristics of R. It's always between or equal to -1 and 1. And it measures how close the dots are to a straight line. The sample correlation coefficient R is an estimate for the unknown population correlation coefficient rho. If you switch x and y, that's not going to change R. If babies that are born after long pregnancies have higher birth weights, that means that babies with higher birth weights tend to be born after longer pregnancies. So the R shows the relationship between the two variables. It doesn't. If you switch if you switch x and y, R is not going to change. It's like I am Dave's brother, and Dave is my brother. The relationship doesn't. If you switch x and y, it doesn't. The relationship doesn't change. If you change the unit of measure, R doesn't change. If pregnancy is long in weeks, it's also the same pregnancy is going to be long in days. The unit of measure doesn't matter. If the baby is it has a high weight in ounces, then the baby is going to have a high weight in pounds. The unit of measure is not going to affect the correlation coefficient. And again, if R is exactly equal to -1 or 1, the dots are exactly on a straight line, and the relationship might be deterministic. It might have happened by chance, but it depends on how big your data set is. But if the data set is small, it could have been on a straight line, exactly on a straight line by chance. If R is close to 1, there's a strong positive correlation, and that means that the dots are close to a straight line with positive slope. The correlation coefficient always has the same sign as the slope. If r is close to -1, there's a strong negative correlation. That means the dots are close to a straight line with negative slope. If r is close to 0, there's several possibilities. It might be the dots are close to a straight line with 0 slope. It might be the dots are close to a curve that's not a straight line. It might be there's no pattern. So there's several possibilities there. Okay, so so we've determined that these dots are fairly close to a straight line. So we want to draw that line, and for right now we're just eyeballing it, and then later we'll get into how to precisely determine the best fitting line for this data set. So I draw dots for the line. Typically some of the dots will be above the line, some dots below the line. So we don't want to, when we're deciding where to put the line, it has to, this is not going to be the line, right? This goes through the dots. We have some dots above, some dots below, but the slope is wrong. And here the slope is still wrong. The slope here has the right sign, positive slope, but it's too steep. Here it's, the slope has the right sign, but it's not steep enough. This is the right slope, but all the predicted values on the line are higher than the actual values. So you want, usually some of the dots will be above the line, some below the line, and the slope should follow the overall pattern. So I drew the line here, and if we extend the line to the y-axis, we can read off the y-intercept. The y-intercept is where the line crosses the y-axis. It looks like it crosses about -110, and that means that b is going to be equal to -110. Okay, that's the y-intercept, is -110. The x-coordinate of the y-intercept is always 0. So we can, in coordinate form, the y-intercept is 0, -110. And then in order to compute the slope, we need a second point. Now, we could, if we pick a point that's, let's say, this point here, a small, if we're off by just a little bit here, it could make a big difference over here. So usually I want to pick a point that's not close to the y-intercept for my second point. And I usually like to pick a point with a number that's easy to divide by. So 40 is easier to divide by than, let's say, 39 or 38 or 37 or even 30. So 40 is relatively easy to divide by, and it's not close to the y-intercept. So I'm going to go straight up from 40 until it hits the line, and then go across to the y scale and read off the y coordinate. So that when x is 40, it looks like y is about 100. Now this doesn't have to be one of the data points. It could be one of the data points, one of the red dots. It could be, but it has to be. More important is that it has to be a spot on the line. It doesn't have to be one of the original data points. So that gives us the second point, 40, 100. Label those x2, y2. And then once we have that, then we can compute the slope. Again, this is just based on the graph, kind of eyeballing the graph to see where the y-intercept was and where second point is. So we can use the letter A or M or B1 for the slope. I'll use the letter A. I like the letter A. Our calculator uses the letter A. So it's y2 minus y1 over x2 minus x1. So it's going to be 100 minus a -110 divided by 40 minus 0. Well, double negative is positive, so it's 100 plus 110 divided by 40. 40 minus 0 is 40. 210 divided by 40, approximately 5.3. And the unit of measure here is always going to be y variable per x variable. It's not really emphasized in if you take intermediate algebra. they give you a formula for the slope, but they don't really tell you that in word problems the slope represents the rate of change. In this case, it's going to be ounces per week. It's y variable per x variable. So on the average, the baby gains about 5.3 ounces per week. Okay, so that's our slope, and then we can plug into the equation y equal mx plus b, or y equal ax plus b. With the y variable is birth weight, our slope is 5.3, x variable is gestation, and the y-intercept was -1/10. So now we can use this equation to make predictions. So for Quincy was born after 39 weeks, so Quincy's predicted birth weight, sometimes they call it y hat. Y with the hat is the predicted birth weight. It's 5.3 times 39 minus 110. Just plugging into this equation, replacing gestation with the x variable gestation with Quincy's gestation, which is 39 weeks. So if we do this computation, 5.3 times 39 minus 110, I get 96.7 ounces. So the residual, or the prediction error, is the actual minus the predicted. So the Quincy's actual birth weight was 104, and the predicted was we just predicted was 96.7. So that's the actual minus the predicted. So 104 minus 96.7 is not 7.3 ounces. So that's the prediction error, or the residual. Later we'll do this with the more precise numbers, using the formulas rather than the graph, and we'll get a better prediction. This is a closer prediction. But anyway, we can compute the residual for each baby, so for Quincy we predicted our residual, or prediction error was off by 7.3, but anyway, do the same thing for each baby, and the best equation, the sum of the residuals should be 0. I think this is not the best equation, because the sum of the residuals is not going to be 0. But the other criteria is the sum of the squared residuals have to be the smallest. For the best equation, that you get the smallest sum of squared residuals. So if we square these residuals, Quincy's residual is 7.3, and then square that, we get 53.29, and do that for each of these babies. Square the residuals, add them up. We get a total sum of squared residuals of almost 700. And later we'll see that the best fitting line has a total sum of squared residuals of just a little over 400. So that's the sum of the squared residuals is sort of the criteria that's used for evaluating the best, which line is the best fitting. Okay, so we can also check the work on the calculator. This will give us a more accurate answer as for the best fitting line. But you want to push clear while holding on, and then push the clear button. So it's hold the on button down and then push clear, and it says mem cleared, and then push clear again. And then you want to do second, hit the data key, and the stat menu will come up. So we push second and then data, the stat menu comes up. And we want to push the right arrow because to get the two variable statistics. We want the right arrow here, and then push equals, and then data again, and then you type in the data. Let's say x1 equals, put in the first x value, and so forth. 39 down arrow, 104 down arrow, 40 down arrow, 100 down arrow, 32 down arrow, 64 down arrow, 41, 120, 38, 92, 40, 110, 42, 122, 38, 96, 41, 100, 39, 112. Okay, then you push, once you get all the data in, then you push stat var, the stat var key here, and it'll say n is 10. And if you push the right arrows, you'll get the one variable statistics, and then you keep pushing the right arrow, you get eventually get the two variable statistics. It's a little bit quicker if you go to the left, push the left arrow. If you push it 3 times, 1, 2, 3, that'll give you the correlation coefficient R is 0.9. It's very close to 1. And then you push it again, it gives you B, negative 109.7 something. That's very close to what we had eyeballing it. And then push the left arrow again, it gives you A, 5.42 something. And our slope is a little off. We had 5.3 for a slope, but so our slope is off. So if we use this, these numbers here, our equation becomes birth weight is instead of 5.3 times gestation, it's 5.42857, etc. times gestation, and we'll get more accurate predictions. We'll get into more on the sort of the this way of doing it in a different lecture. Okay, so just some terminology. The x variable is generally the independent or explanatory variable. If you think one variable may cause or affect the other variable, that will be the x variable. If one variable comes earlier in time than the other variable, the one coming earlier in time will be the x variable. The other one would be the y variable. Sometimes it's kind of hard to say which variable might affect which variable or which one comes first in time. So it's sometimes it's a little bit arbitrary. You can actually if you're just doing the correlation coefficient, it doesn't really matter. The only time it matters is if you're doing the regression. Then it makes a difference which variable is x and which variable is y. The y, once you decide on the x variable, the other variable will be the dependent or response variable. There are if you go on to other statistics courses, there are ways of doing regression for more than just 2 variables, but we're just going to do it for 2 variables. You can write equations for 2 or 3 or 4 or 5 variables or more. Okay, so that concludes this presentation.